All the trends and exceptions when it comes to inorganic chemistry, I'm going to give you in this particular session. From this session, you can expect 2 to 3 questions for sure in the upcoming NEET examination. And the session is going to be short and precise. Watch it till the end. My dear students, what all trends are there? What all exceptions are there? Let's get to know when it comes to inorganic chemistry. First of all, I'm going to give you the order of the boiling points and melting points. My dear students, the first thing which you need to remember, when it comes to group 13 and group 14 elements, the general trend says that down the group, melting and boiling point decreases. When it comes to 15, 16, 17 and 18th group, the general trend is your melting and boiling point, they increase down the group. So for 13 and 14th group, melting boiling point decrease down the group. For 15, 16, 17, 18, your melting and boiling point, they increase down the group, right? Now, if you look at the order of the boiling points and the exceptions, first of all, group 13, group 14, there is no exception. Down the group, as you can see, your boiling point is decreasing, right? Group 15, group 16, there are exceptions. First of all, down the group, your boiling point increases, but there is a change here. Antimony should come here, bismuth should come here. So here the first exception comes. In group 16, down the group, your boiling point increases. So it is increasing, but at the end, before tellurium, polonium comes. Then group 17 follows a normal trend, right? Down the group, boiling point increases. Group 18, down the group, boiling point increases, no exception. So when it comes to boiling points, 2 exceptions are there. One is group 15, one is group 16, and that too at the end. Number 1. Number 2, when it comes to the melting point order. My dear students, first of all, it is full of exceptions, I must say. Yeah. First of all, in your group 17 and group 18, there are no exceptions when it comes to melting points. As you can see, down the group, melting point is increasing. Down the group, melting point is increasing. But 13, 14, 15, 16, there are some exceptions, right? See, in your group 13 and group 14, your melting point, that decreases. That's the general trend, right? So boron, aluminium. Now gallium should come. But gallium and thallium, they are interchanging the positions. So 3 and 5 you have to interchange here. Similarly, group 14, generally what happens? Down the group, melting point in group 14, what happens to that? That decreases, right? But here you have to interchange 4th and 5th element. This is 1, 2, 3, 4th and 5th. That means tin and lead you have to interchange. So lead comes first, then comes your tin, right? Similarly, group 15, 3rd and 5th position you have to interchange. First of all, you know down the group melting point increases in group 15, in group 16, right? In group 15, down the group melting point increases. Perfect. So the order should be nitrogen, phosphorus, arsenic, antimony, bismuth. But you have to interchange the elements 3 and 5, right? You have to change the elements 3 and 5. So technically, antimony should come here, bismuth should come here, but the order is reversed. Similarly, group 16, you have to interchange 4 and 5th element. You know, down the group, melting point increases in group 16, right? So technically, the order should be oxygen, sulfur, SETEPO. But these 2 elements you are interchanging at the end. And there are no exceptions in group 17 and group 18. They are following the general trend. Talking about the next one. Talking about the trends in oxidation state. My dear students, group 13, group 14, group 15, group 16. What you have to remember? When I talk about the group 13 element, the lowest oxidation state shown by group 13 is +1. The highest oxidation state shown by group 13 is +3. Similarly, lowest oxidation state shown by group 14 is +2. Highest oxidation state shown by group 14 is +4. Similarly, group 15, lowest +3, highest +5. Lowest +4, highest +6, right? Similarly, the negative oxidation state shown by group 14 is -4, right? The negative oxidation state shown by group 15 is -3 and this -2. Now, there are 2 things which you need to remember. My dear students, these are the lowest oxidation states. This is lowest oxidation state of group 13, lowest of group 14, lowest of group 15, lowest of group 16. And remember, the stability of lowest oxidation state, increases down the group. Whether you talk about group 13, group 14, group 15, group 16, right? So what is the lowest oxidation state of group 13? That is +1. So down the group in group 13, the stability of lower oxidation state increases, right? Similarly, down the group, when I talk about group 13, for example, its highest oxidation state is +3. Group 13 shows highest oxidation state of +3. But down the group, the stability of highest oxidation state, that decreases. Be it group 13, group 14, group 15, etc., etc. Right? Moving on to the next one. Order for back bonding. My dear students, BF3 shows maximum back bonding because there'll be 2p2p overlap, right? Followed by BCl3, BBr3, Bi3. This is the order of the back bonding, right? Whatever is going to be the order of back bonding, reverse to that is going to be the order of Lewis acidic strength. Reverse to that is going to be the order of Lewis acidic strength, right? Order of atomic radius. Order of atomic radius. You have got group 13 elements: boron, aluminium, gallium, indium, thallium. So you know, down the group, what happens to radius? Generally, down the group size increases. Down the group size increases. So order should be boron, aluminium, gallium, indium, thallium. But over here, there is an exception, right? Gallium comes first, then comes your aluminium. Why is that? Because of the pore shielding of the orbitals. You have studied it, I believe. Now, again, the atomic radius order. Remember, from 3D to 4D, 4D to 5D, down the group, size should increase. Size should increase. So 3D elements have got lesser size than 4D and 5D. But remember, 4D and 5D, they have almost equal size because of the lengthened contraction. Similarly, atomic radius, when it comes to the 3D series. Perfect. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So from scandium till manganese, what happens? Size decreases. Size decreases. Then cobalt, iron, cobalt, nickel, size almost remains the same. Then again follows the same trend. Okay. What is the reason? Reason is from here to here, Z effective dominates over screening. Right here in these three elements, Z effective and screening is almost equal. And right here in the last case, screening dominates over Z effective. Perfect. You would have studied this, I believe. And I have taught you this in periodic classification as well. Now the order of ionization energy. Order of ionization energy. When it comes to group 13 elements, my dear students, group 13 elements. In group 13, I would say, boron has maximum ionization energy. Then comes your thallium. Then comes your gallium. Then comes your aluminium. And then comes your indium. So this is the order of the ionization energy when it comes to group 13, right? Group 14. Generally, when you move down the group, ionization energy decreases down the group, right? So carbon has got maximum, followed by silicon, followed by germanium. So tin should come, then lead should come. But over here, it's again interchanging because of the pore screening of D and F. Perfect. Now when it comes to the ionization energy of second period. Along the period, my dear students, ionization energy generally increases. So lithium, beryllium, boron, carbon, nitrogen, oxygen. But over here, these two elements have been interchanged. And right here, these two elements have been interchanged. You already know the reason. When it comes to beryllium, completely filled orbital, right? To take electron out from here, more energy is required. In nitrogen, half-filled configuration. To take electron out from half-filled configuration, more energy is required. So this is the actual order. Similarly, 3D series, right? 3D series. What happens generally when you move from left to right? What happens to ionization energy? Ionization energy increases. So scandium, then titanium, vanadium, manganese, iron, cobalt, nickel, copper, zinc. But 2, 6, and 7, the sign changes. 2, 6, and 7, sign change. Generally, what should be the sign? Sign should be like this. It should be like this. It should be like this, correct? Because on moving from left to right, ionization energy increases, correct? But you have to interchange the sign at position number 2, at position number 6, 1, 2, 3, 4, 5, 6, right? And at position number 7. Perfect, you have to interchange them. You have to interchange the signs. Reason is again the pore shielding of d electrons. Now, electron gain enthalpy order. Down the group, what happens to electron gain enthalpy? Electron gain enthalpy down the group decreases. Perfect. So oxygen should have maximum electron gain enthalpy in its group, but it has got the minimum, right? It has got the minimum. What is the reason? Reason is its smaller size. Perfect. Because of which it experiences more repulsions when incoming electron comes. Similarly, group 17. Group 17. Generally, down the group, what happens to electron gain enthalpy? Electron gain enthalpy decreases. Perfect. So that means chlorine should have less electron gain enthalpy than fluorine, but chlorine has got more than that of fluorine. Why is that? Because fluorine has got lesser size, repulsions are more. Acidic strength order. Generally, acidic strength is directly proportional to oxidation state of central atom. If the central atom is same, right, as you can see in this particular case, more the oxidation state of the central atom, more is going to be the acidic strength. More the oxidation state of the central atom, more is going to be the acidic strength. But this is valid only when the elements are same. When the central atom is same. And when the central atoms are different, then acidic strength is directly proportional to electronegativity. More the electronegativity, more the acidic strength. As simple as that. Moving on to the next one. Hydrides of group 16. Hydrides of group 16. Like H2O, H2S, H2SC, H2T, H2Pu. Right? What is the bond dissociation energy order? Simple, no exception. Down the group, bond dissociation energy decreases. Why is that? Because size increases. Because down the group, size increases, correct? More the size of the atoms, lesser is going to be the bond dissociation energy. So down the group, when it comes to the hydrides of group 16, I would say bond dissociation energy decreases. No exception in that. Similarly, stability. Whatever is the order of, remember, stability is directly proportional to bond dissociation energy, right? So whatever is the order of bond dissociation energy, same is the order of the stability. Perfect. Acidic strength. Your acidic strength and reducing power, they show the same order. Acidic strength and reducing power, they show the same order, and the order is reverse of these two. Order is reverse of these two. It's pretty much simple. See, H2PO, its bond dissociation energy is least, so it will give away H positive easily. It is going to give away H positive easily. If it is giving away H positive easily, that means it's going to be more acidic for sure. And whatever is going to be the order of acidic strength, same is going to be the order of reducing power. Similarly, hydrates of group 17. When it comes to bond dissociation energy down the group generally decreases because the size of atoms is increasing. Perfect. And stability is going to follow the same order as shown by bond dissociation energy. Now, acidic strength and reducing power, they are going to show the same order, but reverse of what was the order of bond dissociation energy and the stability. And the reason is same. Similarly, bond dissociation energy. In case of Cl2, Br2, F2, I2, generally what should happen? F2 should have maximum bond dissociation energy, followed by Cl2, followed by Br2, followed by I2. Why F2 comes at the third position? Because of the smaller size, repulsions are more, bond dissociation energy is less, comparatively, compared to Cl2 or Br2. It goes to the third position. Remember this particular order as well. This can be asked. Reactivity order. Remember F2 will be maximum reactive, followed by interhalogen compounds, followed by Cl2, Br2, I2. This order can be also asked, right? So first is going to be F2, which is going to be maximum reactive. Then interhalogens will come at the second position. Then Cl2, Br2, I2 will follow the general order. And my dear students, these are some very, very, very important trends. Perfect. Anything can be asked out of these trends, but please remember them, go through them once again, right? And I'll be sharing the PDF of this particular session on my Telegram, which is Wassim Bhat Chemistry Official. That's the name of the Telegram channel. And this is the Telegram channel link as well. Perfect. Do join the Telegram. I'll be sharing the handwritten PDF of this particular session, right, in the Telegram right after this particular session. So with this, I'll be taking leave. You take care. God bless you all and love you all, guys. Bye-bye.